Hi there! We are going to talk about a theorem, a beautiful theorem in mathematics called Theorema Egregium, or it really means remarkable theorem, by Gauss, the great mathematician. It is indeed like Gauss telling us, behold curvature. Why is it important? Why is curvature an important concept? Indeed, because it is started together with a generalization made by his student Bernard Riemann, another great mathematician, a whole new world in mathematics, the mathematics of non-Euclidean geometry, or things like this, differential geometry. There is another reason, which is somehow more interesting for us. It was later revealed by Albert Einstein that the world is governed by general relativity, and general relativity is indeed a theory which is based on the concept of intrinsic curvature. So that's the interesting part of the story. And there is also another thing we can say. Math is in some sense the investigation of invariance. Invariance is something that does not change during some other process. Some translation, some rotation, something that changes the shape or the arrangement of numbers. But if something here is unchanged, we call it an invariant. And in this theorem, we found that there is something very important called curvature, which is invariant of many deformations. So, what does it really say? What does this theorem really say? It simply says that curvature exists. Or in mathematical terms, we can say it says curvature is a well-defined concept. To put it in other words, equivalently, we can say that Gaussian curvature of surfaces does not change in bendings. But in this technical definition, we have to define a number of terms like Gaussian curvature, bending, and things like this. So let's go inside the subject and define the concept. We have a number of concepts here. Gaussian curvature, spherical image, which we need for Gaussian curvature, and bendings. So, what is a spherical image? Think about a surface here we have with 4 arrows on it, blue, green, red, and yellow, with the area A. All arrows have unit length, and all of them are perpendicular or normal to the surface. Now consider that we have a sphere with radius 1, with unit radius, and in your mind translate all of those arrows which are perpendicular to the surface and put them in a way that the beginning of these arrows would be in the center part, in the center of the sphere, without changing their direction. So we have translated them totally parallel to what they were first. Then we have 4 new points on the surface. For not confusing and for not introducing many names, I prefer to use colors instead of names. So the red arrow there would be the red arrow here. Then we have 4 points on the surface of the sphere. Now, these 4 points can be connected to each other by portions of great circles. What are great circles? Great circles are the greatest and biggest circles that can be drawn on a sphere. Or in other words, they can be defined as circles that are made by intersection of a plane with a sphere if the plane goes through the center of the sphere. So we have 4 portions of great circles which connect those 4 points on the sphere. And now we have something which is called a spherical polygon. It means it is on a sphere and it has some edges, so we have a 4-sided spherical polygon. And the area of this polygon on the surface of this sphere has the value S. The area of the first surface had the value A. So right now we have the capacity to define the Gaussian curvature. Let's go to it. So what is Gaussian curvature? So simple. It is just a fraction S over A. Let's go again to where we started to define the spherical image. If you look at this shape, if the original shape is a little bit more curved, then the 4 points on the spherical image would be more far apart. On the other hand, if the surface is totally flat, all these normals would be the same. They would be parallel. And then the 4 points on the spherical image, then they become 1 point. And it means the area would shrink, the area S would shrink to 0. And it means this fraction, Gaussian curvature, would simply go to 0. And it means flat surfaces have 0 curvature. That's exactly as we expected. Now there are hundreds of videos on YouTube telling you that how this curvature behaves and how it changes when we change the surface, the original surface. I think there are very good and brilliant material about the subject, so we are not going to put any more time on that. Instead, we would go directly to the theorem, for which we need another mathematical definition. Bendings. What are bendings? Bending in general means reshaping a surface, generally a curved surface, without ripping or stretching. So, what does it mean to bend a surface without ripping or stretching? Look at this paper. I have it here. This paper is generally flat. Okay, I understand what it means to be flat. Now, if I make the surface to be rolled like this into a cylinder, then I have performed a bending because no ripping or stretching has happened. We know papers cannot endure ripping or stretching. Or if I bend it like this, or make it like a cone, like this, all of these movements, all of these performances, they are bendings. But if, unfortunately at this part I have to destroy this beautiful paper, but if we try to make it like a part of a sphere on my fist, you see that there are hundreds of wrinkles on the surface. Or if I would try to make some other reshapings, it would be ripped or stretched. So that's not a bending. So there is another definition for the bending performances or bending transformations, and it would be like saying that the bending keeps the length of all curves on the surface and it doesn't change them. It really says that if you have a paper like this and you draw a curve on the paper, whether it is straight or it is another curve on the paper, if I make it like this, the length of these curves would not change. But if I rip the paper, the length the length of these two curves would definitely change. So, bendings are transformations which keep the length of all curves on the surface, and the word all curves is really what we need here. Now, Theorema Egregium states that during a bending, S over A is kept invariant. That's its technical definition. So, we go directly to the proof. Step 1. We should approximate a convex surface like this with something like this. This shape is a pyramid-like shape, and I think these 4 arrows with their colors show us that what we are talking about, and those 4 points with their colors show how we approximated the first surface with the second surface. Step number 2. Follow the spherical image of the pyramid-like shape. So, here we have this pyramid-like shape. Look at it. It has 4 colors. For example, here it is orange and the arrow has the color orange. It means this arrow is perpendicular and normal to this side. And yellow and green and red and pink. So we have it. Now we have to look at the spherical image of this shape. This shape is something a little bit strange. Look at it. If I make it like this, flat like this, then all of the 4 arrows would point in the same direction. But indeed, we cannot make it like this. That's because it's an approximation of the original surface, and the original surface cannot be totally bent in this theorem. There must be some limit points which are not included here. So, look at this. If I make this maneuver, if I change it like this, the 4 arrows would change their direction. You see it? Now, we have to think and we have to investigate how would these 4 arrows change their direction on the spherical image. And the spherical image made by these 4 points, how would it be and how would its area would be? Indeed, what we are going to prove is that during this maneuver, this dance of arrows, the spherical image of these 4 points would be kept and it would not change, which is something very remarkable, and that's why they call it remarkable theorem. Step number 3. We have to show that the inner angles of the spherical polygon is preserved. And how is it possible by that very interesting dance of arrows? How would it be that these 4 angles would be kept, would be fixed during these dances? That's exactly our task. We have to prove that, we have to show that. Step 4. We can use Girard's theorem, which is in our case saying if inner angles of a spherical polygon are unchanged, then the area S is unchanged. That's a beautiful theorem, and there are bunches of videos about this theorem. It has a very simple proof. I think you can find it on YouTube, so we do not put time on it. We just want to show that this theorem here holds, and the inner angles of our spherical polygon here will not change. Now we go back to step 3. Step 3 must be thought of as 3 stages. First, the shape has only 1 degree of freedom. What does it mean? It means, look at this. It has many maneuvers, but if we do not think about solid changes, like here, here, for example, this is a rotation or this is a translation, if we do not think about them, and in a spherical image we do not really think about them because all arrows are simply put in the center of the spherical on the sphere, then this shape has only 1 degree of freedom. Whether I make the transformations like this, or whether I keep one of the colors, for example here red, fixed, and I change the others, there is only one way. And by one way I mean that here at the rear part, at the back, I have made 4 angles to show that, for example, the angle between red and pink, it is here by this paper green. For example, right now it is about right angle, 90 degrees. So if it is 90 degree, then the whole shape is fixed. It cannot have any other configurations. So it has 1 degree of freedom, which means, for example, if I fix this angle, this green angle, to 30 degrees, then the shape would be a solid shape. Nothing would change. If it is 100 degrees, it is another solid shape. So the shape has only 1 degree of freedom, and rotations and translations do not matter. So we can say that we are allowed to fix one direction during the bending, for example here, and then change the other sides, make the maneuver, and the result on the spherical image is exactly the same as we would change all of the 4 directions simultaneously. So here we have a maneuver in which all of 4 arrows change their direction. But here is a maneuver that the red is fixed and the 3 other arrows change their direction. So if the shape has 1 degree of freedom, which in our case holds, then the maneuver are exactly the same. So if we prove that during one of them the inner angles of our polygon on the sphere is unchanged, then during the other maneuver the inner angles of our polygon is unchanged. That's because they only differ by rotations and solid transformations, because this shape has only 1 degree of freedom. Now, look at the spherical image of this shape. You can see the colors of arrows, and you see an angle theta on the picture. The angle theta is formed by 2 portions of great circles, one of which connects pink arrow to the red arrow and the other the red arrow to the orange arrow. Now what we are going to show is that this angle theta is preserved during this maneuver in which all arrows move except red arrow. Now I think it is somehow clear from the image that why is it preserved, but we are going to explain it. Yeah. Look at this black line. This black line is the intersection of the pink plane and red plane. So what does it mean? It means that whatever happens, the red, if I move a little bit the red arrow closer to the black line and the pink arrow closer to the black line, whatever the shape is, the pink and red arrows are perpendicular to the black arrows. It means if the red arrow is fixed, and of course black arrow is fixed in the space, when it rotates, when the pink arrow rotates, it makes a rotation around the black line perpendicular to it. So in the spherical image, you see that the black line is preserved, the direction of black line is preserved, the direction of red arrow is preserved, and since the red and pink arrow are both perpendicular to the black line, it means that pink arrow will move along one and special great circle. So the pink arrow does not move arbitrarily on the surface of the sphere. It just moves along one single great circle. And the surprise is that the same holds for the orange arrow. You see that the orange arrow moves along the same great circle that it was on. And the first, when we hadn't moved, we hadn't reshaped the shape. So we see here that two arms of theta indeed are preserved, and the pink and orange points move in a way that two great circles do not change. So here the proof completes. Red arrow is not any special arrow. Every one of those arrows can have the same argument, so we can say that, for example, fixing the pink arrow and moving all the others, they move in a way that the angle on the pink point would be preserved. And don't forget, this shape has only 1 degree of freedom, which means proving the situation for one case proves the situation for others. And that's exactly what we are seeking. This maneuver keeps the angles, and it means by Girard's theorem it keeps the area of the spherical image. And since the Gaussian curvature is the ratio of Gaussian image, area of Gaussian image, to the area of the original surface, it means that the Gaussian curvature is invariant under these bendings. Thank you very much.